that we've given you a little background of radioactivity, we can move into the experiment that really defined the nuclear atom. Remember, this is a continuation of atomic theory, the idea of what an atom is, what it's built like. And so to say that the nuclear atom was described after this experiment is to say that the idea of the atom now included a nucleus. Right? We know pretty across the board that atoms have nuclei, and that's where the protons and neutrons are. But that was not known at the time. But in 1911, Ernst Rutherford in England, he was a pioneer in radioactive studies. In fact, I believe he had actually already won a Nobel Prize for his studies of alpha particles, alpha decay. And using his radioactive skills, he decided to carry out experiments to test Thomson's plum pudding model. Remember the plum pudding model thinks of an atom. It still thought of an atom as a sphere, but there were these negative parts, these negative electrons spread throughout, and kind of like a diffuse positive matrix. Kind of, you think of it like a blueberry muffin, where the blueberries are the electrons, and the rest of the muffin is whatever the positive stuff is. And so Rutherford wanted to test this model, this idea. And so because he was an expert in alpha decay, he had the capacity and the knowledge to direct alpha particles at a thin sheet of gold foil. He thought that if Thomson was correct, then the massive alpha particle, right? Remember, it's the largest form of radioactive decay, right? It's the largest particle of radioactive decay that can be emitted. Now, that if Thomson's plum pudding model was correct, then the massive alpha particles would blast through the thin foil like cannonballs through gauze. But in fact, the very first iterations of this experiment were not actually carried out by Rutherford himself. They were actually carried out by a pair of graduate students that were working under Rutherford. Some pretty famous guys, Geiger and Marsden. They were actually doing the first several iterations of the experiment. And so he expected that the alpha particles to pass through this sheet of gold with minor and very infrequent deflections. Now, coming up into this experiment, Rutherford had this idea, and it was kind of a hypothesis that he was actively testing with this experiment, is that most of the atom is empty space. And so he wanted to test that. He wanted to see how often something, a charged something, or even a physical something, would deflect or have something bounce off of it within the atom. So he figured this very large alpha particle would either bounce off of something or go straight through because it hit nothing, right? And his hypothesis is that it would go straight through because there'd be nothing to hit. Remember, his hypothesis was that the atom is mostly empty space. And in fact, when they actually ran the experiment, right? So here's a little depiction of the experiment. Here's the source of the alpha decay, and so the alpha particles, are shot this way. Here's the little gold foil. So these paths of the alpha particles down here were the expected paths, right? Straight through or with minor deflections, right? And they would be pretty occasional, not that frequent. What Rutherford did not expect are these deflections that come out at wide angles, especially the ones that came back. Right, the ones that really alarmed Geiger and Marsden, the guys who were actually carrying out the experiment in the first place. It was the ones that came back towards the source of the decay is actually what really got their attention. And so they brought these results back to Rutherford, and he didn't believe them. He thought that they had set up the apparatus incorrectly, that they hadn't followed proper protocol. So he just told him to do it again. And in fact, most of the alpha particles, they were passing straight through, but there were alpha particles that deflected with a large angle. So this would be the large angle deflection. And then some were even reflected, right? This would be the reflected ones, the ones that come back towards the source of the emission. So when Rutherford finally got up and went down to the lab, he saw that this was the case, that most of the alpha particles did pass straight through, but many were deflected at large angles, and some were even reflected. His comment at the time was that this behavior was like shooting a howitzer, which is kind of an old-timey rapid-fire gun with large shells. Rutherford said that it was like shooting a howitzer at a piece of tissue paper and having the shell reflected back. Right? It was not what he expected. He expected the atom, what he was shooting these alpha particles at, to be mostly empty space, to have very, very small particles called electrons somewhere in there, and if they came into close enough contact, that would cause a deflection, right? The charge would cause a bending of the path, but nothing massive enough to cause this very, very large alpha particle to bounce backwards, right? That was not in their mind. That blew their mind. So this caused Rutherford to conclude that the plum pudding model could not be correct. Now, again, not to say that the plum pudding model was, useless or should never have been. This is an example of adding new information to the, collective knowledge set, the collective information set, and so we have to change the model. We have to make adjustments to the way we think about reality. So those particles with large deflection angles had a quote-unquote close encounter with a dense positive center of the atom. Those that were reflected, remember, these ones that went straight back, would have had a direct hit, right? They would have hit directly off of this center, this highly positive center. Now, when we say deflections, we're talking about, see how this arrow has a small, it kind of changes its direction just a little bit, right? This was expected, but not this wide angle deflection right here, and not this reflection right here. And so, in order to explain these results, Rutherford conceived the nuclear atom, meaning that there was a dense, positively charged core. And at the time, he used the word nucleus. Now, one of the reasons that the word nucleus was used is because at the time, the microscope had been invented a few years prior, and so lots of studies utilizing the microscope was going on, especially botany, right? Looking at things, plants through microscopes. A lot of study going on at this time, and I believe it was actually a cork. It was cork. One of those early scientists commented that he was actually looking at the remnants of cells, like the cell wall, and so he saw that they were little components, right? And so that's actually where we get the name cell. But in that field of study, this idea of having a nucleus, right, nucleus of a cell, is a very scientific term, as opposed to today where we use phrases like it's the nuclear family, which is fair enough. But back in this day, that kind of colloquialism didn't exist. The word nucleus was kind of, it belonged to the scientific community. So Rutherford used the word nucleus to describe this central, highly dense, positively charged nucleus. And through some further experimentation, Rutherford found that this center contained most of the mass of the atom, while the remainder of the atom was in fact empty space, like he had originally thought.